All right. See if this is working. Okay, it is. So in lab this week, we designed an op amp, and one of the most important specifications we wanted to hit were an open loop gain of, I think it was 40 dB or more, a gain bandwidth of 10 megahertz or more, and then an output signal swing of at least 0.5 volts peak to peak. So I don't think we've really talked much about how to simulate these things, and I don't think you guys covered it in 330 either. So I'm going to make one or two quick videos here about how to simulate these things. I know in lab, everyone was able to simulate their open loop gain and gain bandwidth. However, I think each lab group used slightly different methods, and there are multiple methods that you can use. But after speaking with Dr. Geiger, we've settled on a method that we would prefer you guys to use for simulating this, and I'm going to show that here. If you have already done if you've already done the method using the stability simulation, then just use that for this lab. Don't worry about redoing anything. But going forward, this is the method that we would like you to use. So here I have this 5T current mirror, or not current mirror, but 5T current mirror load op amp that I've designed. I'm not showing the widths and lengths just because I don't want you guys copying it. And I want to simulate sorry, I'm a little tired. I want to find the small signal characteristics of this. So you can see I've created all my pins, and I've already created a symbol for it, which you can see right here. And so now I need to create a test bench. So you guys all know how to create a new cell. I'll make a schematic. Oops. I'll call this op amp small signal test bench. Okay. And in this test bench, the first thing you need to do is instantiate your op amp. So here's my op amp. And I'll just run through this real quick. I'm going to set up all my sources. So VDD, VSS, VB2. You can skip forward a little bit. This seems redundant. I just wanted to go through it with you guys step by step. So I'm going to use the VDC. I really like this VDC source more than the V source that you guys use. I just think it looks nicer. It's simpler. I think you can use both, but I'll be using this throughout this video. So I'm going to set up these sources over here. So this one will be VSS. I'll have a negative. This one will be my VB2, which I set to negative 550 millivolts. Then I'm going to connect all these. I'm going to use this net name GND exclamation point. This is the same thing as just creating the normal ground symbol that most of you use. Both do the same exact thing, just one has a nice symbol and one does not. Okay, so now I have my supplies set up. The next thing I'm going to do is I'm going to add my load. So I'm going to extend this. I name this output. And then I'm going to add my capacitive load. So with an ideal capacitor. And once again, I'll connect the bottom to a ground. Okay, now what we're interested in finding here is the open loop gain and the gain bandwidth, which is the open loop gain times the bandwidth of the open loop response. So we're not going to use feedback for this. Instead, we're just going to give this a common mode signal and a differential mode signal. So to give these signals, I'm going to use two of the VDC sources from analog lib. So I'm going to place one here, one here. And I'll connect this top one gets connected between the VN negative and VN positive. And then the bottom one just goes to ground. And so this is basically doing is our bottom voltage source provides the common mode input, and the top source provides the differential mode input. So for my common mode, I think in our specifications, we said that we're going to have 0 volts. So I'm going to set this to a DC voltage of 0. And then for my top one, I don't want to use a DC input. Instead, I want to use an AC input because we're looking at small signal. And the AC simulation in Cadence basically just solves for the Q point of your circuit, and then it linearizes your circuit using the same sort of small signal analysis methods as we introduced in 330. And then it simulates using the linearized circuit. Um, Hopefully that all makes sense. I can explain it more next lab if it doesn't. Um, but when it's running an AC simulation, it looks for it uses the DC to solve for the Q point, and then it uses AC inputs to actually run the simulation. So for this source, I don't need a DC voltage because I want the DC voltage of these two inputs to be the same. I want them both to be 0. So I'll just leave it blank. It's the same thing as having 0. But I do want an AC input. So I'm just going to use an AC input of 1 volt. It doesn't really matter how big or small this is because the simulator just makes it a linear circuit. And you can make this 0.1 volts and it'll run and have an output. You can make it like 1,000 volts and it'll still have an output because it doesn't take into account the nonlinear behavior of your op amp. It just linearizes it. Okay, so just use 1 volt input because if we use 1 volt input, then whatever our output voltage is will be our gain because output voltage over an input voltage of 1 volt would be the gain, which is just the same as the output voltage. So set it up like that, and then we can check and save, and our circuit is all ready to go. So now I'm going to launch I'm going to create an ADE Explorer view. And in here, I'm going to set up an AC analysis. So click to add analysis, select AC, and we're going to sweep the frequency. We're going to start at a low frequency. So let's say 1 hertz. It can be like 0.1 hertz or 1 hertz. And then I want to be able to see beyond my gain bandwidth a little bit. So the gain bandwidth for a single pole system, which our op amp is a single pole system, should be about the same as the unity gain frequency. So we expect it to be about 10 megahertz. So I'm just going to go 1 decade beyond that to 100 megahertz. So we can put 100, capital M here. And then for the sweep type, never use automatic. Always change this. So I'm going to change it to logarithmic. And then I'm going to give it, you can give it like 10 to 50 points per decade. So I'll just do 50. This might take a little bit longer to simulate, but it's fine. So hit OK. And then now we need to set up our outputs. So what I'm going to do is go over to this little probe button here. I'm going to click on this, and it's going to create an expression. So normally you guys have been taught to use this whole outputs, to be plotted, select on design. Instead, I'm going to set up an expression to grab the output voltage waveform because it just makes it easier to calculate other things, which I'll show you in a sec. So I'm going to click into this details box and click on this little pen and paper on the side. This pops up this window, which I can use to quickly create functions. So it has like a locate function thing down here. But all I'm going to do is I'm going to type VT and click on this guy. So this is going to grab not VT, VF. VF grabs an AC waveform, and then I'm going to go down and find output. And then hit this little green check mark. And I'm going to name this my gain ratio. So this is my gain in volts to volts. Now I also want to be able to see my gain in dB. So I'm going to add another output and go click on this little pen and paper. I'm going to start typing dB20. I'm going to start typing dB. I'm going to find this dB20 function. And then I'm going to type in gain ratio. Click on this. And then add a little parenthesis, and you're good. So now what this is going to do is it's going to grab the gain, or it's going to grab the output voltage, AC output voltage. It's going to call that gain ratio. And then it's going to calculate the same value in dB using this expression. And so I'm going to call this gain dB. And if I run my simulation, Sorry, it's getting a little long. I'm trying to move quick, but and it simulates, and here we go. I can see here is my gain in volts to volts. It won't say volts to volts, but it is. It's your output voltage, which if you put it over 1 volt, it gives you volts to volts. So you can see I have a low frequency gain of like 443 volts to volts. Then down here I have my gain in dB. And so you can see it's about 52.9 dB. And then I want to find my 3 dB frequency or my bandwidth. And so to do that, one way I can do it is create markers. So if I use M to create a marker, and then Q, so I can click on it and hit Q, then I'm going to do X mode and put this at 1 hertz. And click OK. And then I see I get 52.93742 dB. So I can create another marker, then click on it and hit Q. And then instead of doing in this position, I'm going to select Y mode. And then I'm going to do whatever this value is minus 3. So that would be 49.93742. Okay. And that will show me that my bandwidth is 22.845 kilohertz, about. And so I can do this, and then, I could also find at 1 hertz up here my gain and my ratio gain. And I can take this like 443, multiply it by 22.845 kilohertz, and that'll give me my gain bandwidth. Okay, so that's the way you can do this graphically, and you can use these nice graphs for your lab report. But I also want to show you how you can automatically calculate all this stuff, because it just makes your life a little bit easier, especially when you have to simulate lots and lots of op amps. And you'll be doing a lot of op amps this semester. So I'm going to close my results and go back to this calculator window. And I'm going to add another expression. And what I want to find is I first want to find my DC gain in dB. Or I'll do two. I'll do it in dB and ratio. So I'm going to open up this guy again, and I'm going to use this function called value. Okay, and this value function calculates the value of a waveform at the point you specify. So the first thing you need to put in is your waveform. And so I'm going to do gain ratio. Oops. And then for my value, I'm going to put 1 hertz. So that's going to calculate, it's going to return the value of gain ratio waveform at 1 hertz, which will be my DC gain in volts to volts. So I'll click check, and I'll call this DC gain ratio. And then I'll add another one. I can do the exact same thing, value, except this time use gain in dB. And then I'm going to do 1, in parentheses, check mark. Okay, now I'll call this DC gain dB. All right, so now if I run my simulation again, I can see, oh, I messed this up. The dB value calculated correctly. I forgot that this guy is actually complex value, but when it plots it, it gives you like the magnitude. So we need to go back into this function here and do add mag parentheses around gain ratio. Now I'll take the magnitude of that and then find the value. So if I do that, then I get my 443.5 volts to volts and my 52.94 dB for my DC gain. So now I've calculated my DC gain. Now next, I want to calculate the bandwidth. So to find the bandwidth, I'm going to add an expression. I'm going to click into here, and I'm going to use this function called cross. cross calculates the X value of a waveform where the waveform crosses a certain Y value. And so what I want to find is the point on my gain in dB where it crosses the DC gain minus 3 dB. That's the definition of the bandwidth. So the first thing you put in here is the waveform. So I'm going to do gain dB. And the next thing is the threshold. So I'm going to do in parentheses DC gain dB minus 3 in parentheses. Then add a space. And it's going to ask you for which edge. We want to use the first edge. And it's going to be a falling edge. So we're going to pick falling. And the rest of these just for some other fancier stuff. We don't need to worry about this. We're just going to do nil, 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 and parentheses. Should look just like this. Check mark, and we'll call this our bandwidth. Then lastly, I can calculate the gain bandwidth. So I'm going to add one more expression. And the gain bandwidth is going to be the bandwidth. I can add times the DC gain ratio in volts to volts. I hit check, and I'll call this my GB or GB. I'll call it GBW, gain bandwidth. And so now if I run, oops, I accidentally double clicked it. Then it'll give me all these values. And so I see that it gives me a bandwidth of, we'll just look at here, bandwidth of 22.84 kilohertz, gain bandwidth of 10.13 megahertz, DC gain of 52.94 dB, and it gives me the DC gain ratio. And that's how I can calculate this. Now, whenever you use calculations, I always like to double check that it's consistent with the waveforms, because sometimes the functions will work a little bit differently than you think they do. And you kind of have to read up on how they work. But I've already double checked these earlier and they all work. And we saw earlier in the video too, I found like the same bandwidth and DC gain. So that's how you calculate it. And then one more thing you can do for fun, if you want to, is when you're designing, you can use this little spec thing over here. So my DC gain ratio, we said we need at least 100 volts to volts. So in the spec category, I can do this little greater than, and then put 100. And that's going to check, oops, excellent. All right, well, I kind of organized this weird, my bad. I did by value, there we go. Okay, so now it's going to check when you simulate it if it's greater than 100 or not, and it'll tell you. And so I can do that. Likewise, 100 volts to volts gives me 40 dB. So for dB, I can add greater than 40. And I want my gain bandwidth to be greater than 10 megahertz. So I can add greater than 10 capital M. And then if I run one more time, and wait, then you can see it'll show all of these as green. And that means it's in spec. So you're meeting your specs. If it's yellow, it means you're very close to meeting your specs, but not quite. And if it's red, it means you're not in spec. And so that can help you quickly see if your design is matching what it should be or not while you're designing it. So this video got much longer than I expected it to be. I am going to stop it here, and I'll make another short video about running the output signal swing simulations. So yeah, hope this is helpful, and thanks for watching.